Welcome to this presentation on troubleshooting vibration issues in process pipework. Today we will walk through the practical steps defined in Section 4 of the Energy Institute Guidelines, covering how to identify vibration problems, perform diagnostic activities, carry out measurements, and determine corrective actions. This process is essential for preventing fatigue failures, ensuring equipment reliability, and maintaining safe plant operation. Overview and importance. Troubleshooting vibration issues in process pipework is a critical activity for maintaining plant integrity and safety. Vibration-induced fatigue can lead to catastrophic failures if not addressed promptly. The process involves identifying symptoms, analyzing root causes, verifying severity, and implementing corrective actions. A structured approach ensures that problems are not only mitigated but also prevented from recurring. This methodology is particularly important in high-energy systems such as compressor discharge lines, pump circuits, and flare systems, where dynamic forces can amplify structural weaknesses. By following the EI guidelines, engineers can systematically review operational history, conduct thorough inspections, perform accurate measurements, and apply both short-term and long-term solutions. The ultimate goal is to minimize downtime, prevent leaks or ruptures, and maintain compliance with safety standards. Understanding the signs of vibration, such as fatigue cracks, fretting, and audible noise, is the first step toward effective troubleshooting. This introduction sets the stage for a detailed exploration of identification techniques, diagnostic steps, and mitigation strategies that form the backbone of vibration management in industrial facilities. Common indicators and symptoms. Identifying a vibration issue begins with recognizing the physical and operational signs that suggest abnormal dynamic behavior. Common indicators include fatigue failures on main pipework and small-bore connections, damage to supports and instrumentation, fretting marks on pipe surfaces, and leakage or weeping from instrument tubing. Loose bolts and fasteners are another telltale sign, often accompanied by high levels of audible noise or visible pipe movement. Operators may also report concerns based on observations or issues encountered on similar units. These symptoms typically manifest under specific operating conditions, such as high flow rates, transient events, or during startup and shutdown sequences. Early detection is crucial because vibration-related damage can escalate rapidly, leading to costly repairs and safety hazards. Visual inspections should focus on welded joints, clamps, braces, and tubing connections, as these areas are most susceptible to fatigue and fretting. By cataloging these signs systematically, engineers can prioritize areas for detailed analysis and measurement, ensuring that corrective actions are targeted and effective. Physical damage number 1, fatigue failure indicators. Fatigue cracks often appear at stress concentrations such as small-bore connections or welded tees. Repeated failures in the same spot are strong indicators of vibration-related mechanisms. Visible symptoms include cracks on welded joints, broken small-bore connections, instrument failure, and repeated repairs in the same location. Physical damage number 2, support and instrument damage. Supports play a major role in vibration response. Damage or looseness in these components amplifies vibration levels and leads to rapid deterioration of nearby equipment. Typical observations: snapped clamps, failed guides or shoes, vibrating instruments, displaced cables or tubing. Physical damage number 3, fretting and leakage. Fretting happens when small cyclic motion exists between touching metal surfaces. It's both a symptom and contributor to vibration issues. Watch for metal-to-metal rubbing, wear scars, tubing leaks or weeping, black dust near contact points. Physical damage number 4, audible or visible vibration. Human senses, sight, sound, and touch, often detect issues before instruments do. Operators' observations are valuable inputs. Be alert for high noise, resonant humming, pipes visibly moving, rattling sounds. Reviewing history and plant operation, conducting a walkdown and gathering observations. A comprehensive review of plant history and operational data provides valuable insights into the root causes of vibration issues. Engineers should examine previous failure locations, metallurgical reports, and investigation findings to identify recurring patterns. Correlating vibration incidents with operating conditions, such as flow rates, pressure changes, and equipment load, helps pinpoint excitation mechanisms. Reviewing past design studies, particularly those involving compressors and pumps, can reveal whether pulsation or mechanical forces were considered adequately. Historical measurement data, including frequency spectra and amplitude trends, should also be analyzed to assess whether vibration levels have changed over time. This step is essential for distinguishing between chronic design-related problems and issues triggered by recent operational changes. By understanding when and under what conditions vibration occurs, engineers can develop hypotheses about potential sources, such as flow-induced turbulence, acoustic resonance, or structural flexibility. This knowledge forms the foundation for targeted inspections and corrective strategies. The walk-down phase involves a systematic physical inspection of the piping system to identify areas of concern. During this process, engineers should assess whether vibration is steady-state, transient, or random, and determine if it exhibits tonal characteristics. Observations should include whether the vibration appears low-frequency, which often involves large visible displacements, or high-frequency, which may only be detectable by touch. Additional factors to note include impact-type events and elevated noise levels. Identifying hotspots where vibration amplitude is greatest is critical, as these locations often correspond to unsupported spans, small-bore connections, or areas near rotating equipment. The condition of supports, clamps, and braces should be evaluated for signs of loosening or damage. Operator input is invaluable during this stage, as they can provide details about operating conditions when vibration occurs and periods when it subsides. Collecting this information ensures that subsequent measurements and analyses are focused on the most vulnerable sections of the system. Basic vibration measurement techniques. Once potential vibration issues have been identified, basic measurement techniques should be employed to quantify severity. According to EI guidelines, vibration velocity measurements are commonly used to classify conditions into three categories: acceptable, concern, and problem. Measurements should be taken under the operating conditions that triggered the initial concern, ensuring accuracy and relevance. If vibration levels exceed the problem threshold, immediate short-term mitigation is required, and specialist advice should be sought. Levels within the concern range indicate a potential risk of fatigue damage, warranting further investigation and possibly advanced diagnostic techniques. For high-frequency vibrations above 300 Hz or transient events, basic methods are insufficient. Specialized tools such as dynamic strain gauges or modal analysis equipment should be used. Recording data across the full operating envelope is essential for understanding how vibration varies with process changes. This information supports informed decision-making and helps prioritize corrective actions. Short-term measures and long-term strategies. When vibration levels pose an immediate risk, short-term measures can help reduce severity until permanent solutions are implemented. These actions may include adjusting operating parameters, reducing flow rates, or altering compressor load to minimize excitation forces. Installing temporary supports can also provide additional stiffness, but care must be taken to avoid creating rigid anchor points that shift vibration to other areas. All supports should be inspected to ensure effectiveness and structural integrity. For long-term mitigation, engineers should consider design modifications such as adding permanent bracing, changing piping configurations, or installing pulsation dampeners. Continuous monitoring is vital because vibration behavior often changes with operating conditions. Routine visual inspections and periodic measurements should be scheduled to track amplitude, frequency, and pattern variations. By maintaining an ongoing review process, plants can detect emerging issues early and prevent failures, ensuring safe and reliable operation throughout the equipment lifecycle.